Welcome to this week's Crunch seminar. So this week's topics are pretty interesting. The first one addresses climate change, climate change topics, which is actually a very hot topic now. So our first speaker is Wenwei, who would be talking about predicting tropical cyclone intensity using deep learning. Before he begins, let me quickly introduce him to you all. So Wenwei is a data scientist at the Pacific Northwest National Laboratory. He received his master's degree in environmental engineering from Protan State University in 2014. And since then, he has developed interest in applying machine learning techniques to solve Earth system and environmental related problems. He has a broad research interest in tropical cyclone hydrology and computer vision. And with this, I leave the floor to Wenwei. You may want to begin and you may share your screen now. Thank you.
All right. Thanks to George and the panels for inviting me here. And it's a pleasure and honor to be speaking here. And this is about a recently published paper in weather and forecasting. And this really is a group effort by myself, Kartik Balaguru, Andrew August, Nick Lalo, Nathan Hodas, David Judy, so these people are from PNNL, and Mark DiMaria, who used to work at National Hurricane Center. And and the funding agency for this project has been, it received partial funding from the Deep Science Initiative, LDRD, at PNNL, and it received additional funding from Integrated Coastal Modeling Project, which is a multi-program funded project within DOE's Office of Science. And I guess I want to mention that I am in no hurry to quickly finish my slides. So throughout the process, if you have questions, feel free to just interrupt or ask me or send a comment, and I will address as I go through. So do feel free to ask questions even before the end. And so this paper really included two objectives and two experiments, which we will get into a little bit later. So the first experiment is about operational forecasting. So there the real challenge has been forecasting at a longer time span. And so here we chose 24 hours intensity forecast as our predictant of interest. And in the second experiment, we developed a 6-hourly TC forecasting model. And the motivation there was to be able to couple the intensity model with the track model so that we can generate synthetic TCs for climate-related studies, which I will introduce more details about that as well a little bit later. So first, let's look at the landscape of the tropical cyclone intensity forecast world. Why we need to work on it, and what's the state of the art. So the first motivation has been that in the last 30 years, a lot of progress has been made in improving the tropical cyclone track forecast. We have more than 50% error reduction. It has becoming more and more accurate, and the forecast has becoming more reliable. At the same time, only 11% of reduction in intensity forecast errors. So by comparison, that's a big delay, and so there's still a lot of room for improvement. On the right side, you can see that on the right side, the figure, you can see the different models and their performance throughout the years since 2010 to 2020. And the annual forecast error has been averaged and grouped by individual models. And I guess we can go into a little bit of the details about the models. So the first three shapes SHIP and LGEM. These are the statistical dynamical category of models, which uses which all originated from SHIP's predictors. So these can be loosely categorized as one family, and HWFI is a dynamical model which simulate in three-dimensional the atmosphere and ocean component of these very dynamical events. And as you could imagine, to simulate this very turbulent event, you would require very high computational cost, and also to simulate the interface. And lastly is FCL, which represents the National Hurricane Center's official forecast. So the official forecast does not just rely on one single model or the best model to make predictions, but in the recent years at National Hurricane Center, they have discovered that by leveraging predictions from multiple different models, and ideally the models would be highly independent from each other, and then combining all these results using a consensus model, they can generate much better result than any individual one of the model. So therefore, as you can see, probably starting from 2014, this brown line has been consistently reproducing the lowest error than any of the individual models. And then in terms of the individual models, the HWolf, the dynamic model, has been fairly consistently being the lowest error model as well. So that's the best leading model. So the recent improvement in tropical cyclone intensity forecast, although as we mentioned, only 11% reduction, not a lot, it has been driven by the consensus model and driven by the improvement of the dynamic model, which thanks to the improvement of computational resources, allowing us to running more complex and numerical models. So that has been the two drivers of the improvement so far. However, we certainly have reached a bottleneck right now because we have the consensus model there, we have the numerical model, we pretty much can run as fine, almost as fine resolution as we would like. And what next? So inherently, forecasting tropical cyclone intensity is a very hard problem, partially due to we have insufficient observations of what is exactly happening at the tropical cyclone core. There are unknown or unrepresented LC interactions and physics there. And if we don't know what exactly is going on or what's the physics, we cannot represent it in a dynamic model and therefore cannot contribute to the forecast. Additionally, the computational expense for numeric models are very high, and we are I spent years of my early years of my career as a numerical modeler, and I know firsthand of how models are sensitive to the boundary conditions and initial conditions, and to carefully prepare that takes time, and the trial also takes a bit of trial and error, and on top of that, the numerical models are still fairly slow, and then slows down the overall iterations of model improvement as well.
Wenwei, I have a question for you. So,
yeah.
So this plot here, which is kind of really interesting, is it for the same type of tropical cyclones like in the Midwest, or where is it? Is it, or is it the same location first of all, and where is it? Which...
Oh yeah. Sorry, I totally skipped that piece of information. So yeah, so this is only for North Atlantic basin. So this is the Gulf Coast and the East Coast tropical cyclones. And here are some models that National Hurricane Centers use. And yeah, so this is only about the US on both land and ocean. Does that answer your question?
Yes, thank you. Thank you.
Yeah. Yeah, and of course, at other part of the world, there are different models being used. Yeah, and different hurricane centers as well. So yeah, so here we are only looking at the North Atlantics, and we discussed that forecasting tropical cyclone intensity is very hard, and there is a good opportunity. I guess the opportunity also lies in that the family of tropical cyclone models that we discussed, SHIPS and LGEM. So these models, they are one family, and so those statistical dynamic models remains fairly competitive still in the operational forecast. National Hurricane Center use it still. However, they are largely multivariant linear regression-based models. They has been developed maybe 20 years ago, and they are still in use today. And it is surprising that they are still very useful and being proven to be skillful. However, there certainly is the opportunity to use better models, machine learning models, to represent the nonlinear relationship within the predictors. So that's exactly what we are looking at right now here in this study. And also, there's, needless to say, there's a lot of significant social economical benefit of being able to simulate tropical cyclone intensity better. It's a high stakes problem, and it is the biggest natural disaster, I mean, in terms of financial loss in the US annually. So there's a lot of interest, and it also I also have some personal interest. So I grew up in Eastern China, although my hometown is about 4 hours away from the coast. My hometown is probably hit by tropical cyclones every other year. And growing up, I certainly felt the intensity and the threat of it. And what also shocked me is that in Eastern China, the tropical cyclones generally moves fairly slow. It can go 3-4 days into the land and is still fairly strong. So this problem really interests me to how to forecast it better. And our approach has been to focusing on the one of the model. So here we are not focusing on the dynamic model H-Wolf, but instead looking at the statistical based model SHIPS. So there, the first question that I had was to, when we use machine learning or deep learning or to better represent the nonlinear relationship, can we at least prove again that the nonlinear model is better? It has been proved somewhere else, but I guess it never hurt to see firsthand what exactly the result is. So that's how the study was inspired. And first, let's look at the data set that I have available. So we used global data, not only including the Atlantic, but also the Pacific and everywhere else, Indian Ocean as well. And also there's a distinction between, in the climate change world, there's a distinction between the reanalysis dataset and the operational dataset. So all the operational forecasts at National Hurricane Center, when they are making forecasts, they don't have a very accurate estimate of the current state of the Earth system. So they have unreliable data, like unreliable track data, unreliable environmental conditions. And this is the operational data set. That's what is available at the moment of forecast is being made. So we have that, but this is a very limited data set, only about like a few thousand points. And reanalysis is when after the season, generally 1 year after the event, people use numerical models to simulate the condition, trying to reproduce it and incorporating many of the observations to make the best estimate of what that condition could look like. And that's a reanalysis data set. So our study leveraged both the reanalysis and operational, combined them together for our training, which we will look at in the flowchart shortly. But overall, it has about 60,000 data point in our data set. And that's here's the flowchart on the right. And we decided to just start by using multi-layer perceptron, which is
Wenwei, can you go back to the data, please? Because that's an okay. What kind of data do you have? When you say data,
oh yeah,
can you describe a little? Is it like the pathway? You have also the intensity? Do you have the duration? In what form you have this data? Because I can imagine that the data you have now in 1982 are different. And how do you reconcile the fact that you don't have the same data contiguous in time?
Yeah, that's a great question, and I totally skipped the information. So this data set is really SHIPS predictor data set, and SHIPS has been evolving over the years, but the SHIPS model modelers did go back all the way to 1982 and using the reanalysis dataset and reproduce the predictors for their model. And so operationally, their model can only take like 20 predictors because it is a multi-variant linear regression model. So, but their dataset include about more than 100 predictors. So it's essentially tabular data set. And so they use, so these data set are kind of what it include, both include the environmental conditions, for example, the large scale wind speed, not the storm wind speed, but the atmosphere circulation, temperature, humidity, all that type of predictors, and also some of the satellite observations of the storm, and including the radius and other parameters. And what else? Yeah, that's pretty much it. Do you have another question, George?
No, so basically use SHIPS is like post-diction, right? Not prediction, but right, because it's done retrospectively. So therefore, yeah, you have calibrated all these models with whatever data there was, real data. So the model has been calibrated for all these 56,000 cases, right?
Yes. So SHIPS has its predictions based on these predictors. However, yeah, in our model, we are not using their predictions. We are only using their predictors. And I don't believe that they have go back to tune the predictors based on their target.
Oh, I see. Yeah, I see. Okay. All right. Thanks. Yeah.
Yeah. That's a great question. And so that's our data set. And and we just started off, because it is tabular data set, we just decided to start off with multi-layer perceptron as an advanced statistical approach to replace the multi-layer multivariant regression. And we decided to optimize the neural network architecture and hyperparameters so that we fully explore the potential. And also because that the number of samples is still a very big limiting factor. And so we designed a low-yield testing scheme that allows for testing of individual years while using most of the data. So low-yield represent leave 1 year out, and at the same time, we know that by doing that, which essentially is the same as like leave one sample out approach, and then we reserved 2019 and 2020 data as independent test years. So the model have never seen 2019 and 2020, but we use that as our final independent test. And in the flowchart, so yeah, we really started from SHIPS reanalysis and predictors and operational predictors. and also from an independent source strategy, intensity change predictant. And we matched the events and conducted our feature selection process. Mostly we have been just trying to keep all the data that has available for majority of the event. And also one thing unique about our approach is that so the predictors look, the ship's predictors looks like this. So it is available for every 6 hours of the environmental conditions along the track. And so we used the, so ships in the ship's model, they has been averaging, for example, I'm trying to forecast the next 24 hours. So Z combines the from hour 0 to hour 24, there are like 4 or 5 time steps. They average them, these predictors, and make a prediction. So that's the approach they use. But in our case, we only used one time step and trying to use it to predict the 24 hours later. So that's a difference, and we decided on that route based on our initial testing. And we filled the missing values and then derived the tabular predictors and labels in a database. And then in the loyal testing scheme, we essentially pick one random year, for example, 2017, and then we reinitiate the model weight and then completely, and then using the year except 2017 to train the model, and then evaluate it on 2017, and then essentially get the evaluation result. So that's our modeling approach. And I assume that all of you know a lot about multi-layer perceptron already, but still here's the illustration about the very basic theory of what it is doing. So I took those environmental predictors, for example, potential intensity, share, distance to landmass, and all others from ship's predictors as my input. And it really, with each of these hidden layers, it is a combination of linear combination of all the predictors, and then in addition a nonlinear activation function. So through each hidden layer, it represents the dynamics a little bit more complex nonlinear relationship between the predictors. And the benefit is that in the end, it allows for very complex representation of the linear relationship among predictors that probably in other way wouldn't have had that connection in other models. And in the end, we predict the intensity change. For example, what the 24-hour intensity change is. So that's the model theory illustration.
How many inputs altogether?
Yeah, altogether is 121 numbers. I mean predictors, and then we have about 60,000 samples.
Yes, thank you.
Mm-hmm. And yeah, a little bit about the neural network optimization. So we used a Bayesian search algorithm called Python estimator, and as implemented in HyperOp Python package, so it is readily available. And the table shows our search space. We searched on the activation function, number of layers, number of hidden layers for each layer. Yeah, number of hidden. No, oh yeah, hidden layer. Yes, and the learning rate and our batch size. And interestingly, it found some really curious architectures in the end. Yeah, actually, this is a typo. So for the second line says 24-hour model architecture. So that's for the 24-hour model, and 122 is our input. And interestingly, it didn't go really deep. It suggested us to go 2 layers with about 2,000 number of neurons in each layer, and that's it. And the third line is this typo. It's not 24-hour, it's 6-hour model. It proposed a slightly deeper architecture, and it also suggested us the learning rate batch size, and for optimization we just use Atom and ReLU activation. And we also had a L2 regularization to essentially overcome overfitting. So that's the optimization, and let's start to look at some of the results. So we
excuse me, Wenwei.
Yeah.
Hi, this is Panostinis from PNNL.
Yeah.
So do you have any intuition why the architecture is so different between the 24-hour model and the 6-hour model?
I thought about it a lot, and then I couldn't reach a conclusion. So it is really curious. So I can understand that the two models can be fairly, I mean, we are asking them to predict different things.
Right.
So like 24 hours later, it would be kind of highly uncorrelated to the current condition, while the 6-hour would be fairly close to the current condition. Also, at the same time, the in the 6-hour model, we intentionally limited the number of predictors to 9 so that we can easily plug it in a climate model. And because of that, so probably
the function is much more complex because you try with 9 predictors to get the intensity change. So you need a deeper network which is more expressive than the shallower one, which can use 121 as input. I see. I didn't pay attention that you use 9 predictors only for the 6-hour model. So that would make sense why you need a more expressive network.
Thanks for the question.
Okay, thank you.
And then here is the modeling result for the first experiment. And we have seen this figure before on the left, and now we have this MLP prediction result with the shading indicating the strap result from 40 random seeds and combinations. And so what we observe here is that I guess the first comparison should be between SHIPS and MLP. And also, I guess, a divide of the between 2010 to 2018 is the loyal testing scheme. And then after 2018, these are the 2 reserved years of independent test. I guess the first comparison between SHIPS and MLP shows that really quite significantly, about 20% or more, MLP is superior to SHIPS. So that was good. And that's really our first intention, is to have it have better predictions than SHIPS. And the comparison, it also outperform T-SHIPS and LGEM by a significant margin as well in most of the years, in both the loyal testing and independent test. And it's also interesting to compare H-Wolf, the dynamic model, with MLP. And it appears that in loyal testing, we saw some period that MLP performed better than the H-Wolf. But we also know that the loyal testing scheme gave us more advantage because back in 2010, MLP knows the information in the future use future events as a for training. However, HWRF cannot. Also, because of the fact that HWRF has also been improving dramatically since 2010. So probably the reason that we can see some superior performance of MLP, and then their difference becomes smaller. And then in the end, in 2018 and 2019, HWRF performed slightly better, but really curiously in 2020, these two almost performed exactly the same. And remember, this is in the independent test. So this is really interesting. And we are not directly comparing MLP with the official forecast because it has official forecasts have exposed to so much more data, different predictions from models. However, we are fairly confident that if MLP can outperform shapes by more than 20%, outperform the shape and SEM by 5 to 8%. And these are operational models. So then we are confident that it will improve the consensus model at the official forecast. So that's our kind of first conclusion from this comparison, the 24-hour intensity forecast. And also very interestingly is that one of the biggest challenges in the intensity forecast world is that all the models are really, really bad at correctly predicting the rapid intensification events. So for example, in 2019 to 2020, there are more than about 54 tropical rapid intensification event being observed. And what rapid intensification event is that the tropical cyclone going through some rapid changes, and the intensity increased more than 30 knots within 24 hours. So what we see that MLP is, despite still have a lot of room for improvement, gives the most heat comparing to all the models except the official forecast. It also has the least number of misses, and the Gilbert skill score and Pierce skill score are two metrics that are commonly used in predicting real events. And in terms of both these metrics, it is superior than the rest of the model as well. So it has some 5 false alarms. Interestingly, it is less false alarms than the leading dynamic model. So that's a very interesting result. And although the model was not originally specifically trained to predict rapid intensification, but it seems that the model's ability to correctly predict it is fairly significant comparing to other models.
Excuse me, Wenwei, yeah. Another question. Yeah. When you say that the total is 827, and
yeah.
then you say that the hits are 11 and the misses are 39, aren't you missing a lot of other?
Yeah, sorry. Yeah, so the total number of time steps essentially, like how many 24-hour events we are predicting. So that's 800, and inside this 800 there are about 50 are rapid intensification events.
Oh, I see. Okay.
Yeah.
Okay. Okay.
Yeah.
Thank you.
So that's that, and a few more evaluation about the model. So here's a plot of the 24-hour observed 24-hour intensity change, plotted with the forecast error. And really interestingly, that all the models, as has been discussed in previous literature, really suffers from that the model forecast error is correlated with the intensity change itself. So normally we would want a flat line, but they are always anti-correlated. And so we want to improve it by having it slightly more flat. So here's the comparison among all the models. And by far, again, MLP has been performed well in terms of that it is the most flat among all. Those boxes indicate, for example, this red box indicate when the intensity change in reality dropped more than 30 knots. And does the model predict so? If the model does the model actually predict have a positive error more than 30, and then in that case it would not correctly predict these rapid weakening events. So we want fewer numbers in this box as possible, so that the line would be more flat. And so also by far the MLP performed the best in terms both of the rapid weakening events in the red box and the rapid intensification in the purple box. It has the least number of error count. So and additionally, we want to measure the model's independence or degree of freedom. As we mentioned that all those models are going to be fed into the consensus model for official forecast. And we want the models to be independent from each other. We don't want to include two models that are highly correlated. And so here is a heat map of the correlation coefficient of the model bias. And what we observed is that by far the H-Wolf is the dynamic model is probably the least correlated with the rest of the model, which is good because it is a dynamic model, is a different category. And kind of similarly, if we look at this vertical line, MLP is by second the most independent from others. We know that we have the predictors from the ships, so the one of the interpretation is that could it be very highly correlated with ships? And luckily it is not. The correlation coefficient is 0.73, which is still much smaller than the ships and LGEM group. As we can see in this box, they are all above 0.8. So they are highly correlated, but this machine learning model is not correlated with them, highly correlated with them. So that is another encouraging result. And I guess really briefly that we also just applied the fairly standard feature importance ranking method of Gaussian variable importance measures. And what it does is that it gets the absolute value of the product of all the weight that are connected to one predictor, and then ranks the predictors by that. The importance score are scaled so that all the predictors importance score add up to 1. And here there are several surprises and not surprises in the finding. I guess the surprise is that except for the initial intensity, the first predictors, none of the rest are deemed as important predictors as in previous linear regression models. So that is a big surprise. And how could these events, how could these predictors be so important? I mean, they all have a reason why they are important, and that's a reason why they are included in the predictor. However, it's kind of very shocking as well. For example, potential intensity has also been probably the second most important feature in linear models, but here it just didn't get to the list. And the reason was that we know that it is a different method, a nonlinear representation, and at the same time, yeah, so that's most of the reason why we have seen the feature being ranked very differently. We also, but it also provide feedback to the other models. For example, many of the models, because they are limited only using a subset of the predictors due to their model structure. Many of them doesn't include the distance to land, major landmass. But here we show that it is the second most predictors, and this is useful to provide feedback to other models. And and then the second, so that's the first experiment. Let's move on to the second experiment. So there so the motivation was to create synthetic tropical cyclones to better quantify the TC risks. Why do we need to do that? First reason was because the TC observation is very scarce, only 15 storms per year in North Atlantic, and in terms of landfalling events, since 1960, we have less than 300 events. And so we have about 1,000 events in North Atlantic being observed. And of course, like every event, every storm has multiple time steps that provide more samples. And also, you may think about that we have climate models. Maybe we can use climate model generate. It would have produced more tropical cyclones for us to better quantify the risks. But it is not true in reality, because due to the very coarse resolutions in climate models, it actually doesn't resolve tropical cyclone very well. So about only 1/3, it produced about 1/3 of tropical cyclones in the climate model comparing to observations. And therefore, a synthetic approach is needed to provide the abundance of synthetic events, and so that we, for every county, every location, we can have a ensemble of tropical cyclone tracks that pass through, and then we can analyze the angles, the intensity, and everything from there. So that's the motivation. And here is exactly how our second experiment was designed. We purposely only selected 9 predictors, lightweight, and then we trained the model to predict 6-hourly intensity change and coupled it with a track model. So the track model is not described here. It's a physical-based model, but together it produced something like in A, that's the synthetic track samples, by comparing to the observations. So immediately there are kind of still obvious differences between the two, partially because these are randomly selected 100 samples. Also that it seems that the synthetic TCs last a little bit longer than the observed, as the same 100 events on the left, it appears more dense because it lasts longer. However, it kind of reasonably captures the randomness of the event. And also, as the approaches land, they quickly dissipate, just like what happens in the observations. So that is good. And in plot C, we compare the lifetime maximum intensity from both the synthetic approach and the observations. And we can see that it reasonably captures the distribution, and the tail didn't quite completely capture it. But it does predict some quite a few category 5 tropical cyclones. So so the tail would be an area for improvement, but in terms of the maximum, it was pretty good. And then in the last plot, we compared, we selected 51 coastal cities on the East Coast and Gulf Coast, and then counted the synthetic landfall versus the observed landfall. So by comparison, within these 50,000 synthetic events, we are able to see that the landfalling count at coastal cities are fairly good correlated. We wouldn't want it to be 1 because we already know that observed events are not sufficient to do these statistics. However, we are glad to see that it is still correlated well. And we can also see the power of using this synthetic approach. We can have, for example, in particular cities, 1,000 or 2,000 landfalling events versus having like 90 landfalling events. So that's part of the result. And I guess this plot shows the comparisons between the track density observations in A and B. There are some obvious differences as well, but overall captures the big picture. And what we are going to apply it is that not just to take the model density as is, but to subtract the track density from two different climates. Then therefore, although we know that the track density will probably have some bias, inherent bias, that is hard to quantify. However, we would have higher confidence in the difference between two climates. So that's the power of the approach. And in CN, we compare the travel time between making a landfall, and it seems that synthetic approach expanded the available of data point and provided a more complete picture of how long does it take for a track to make landfall. I mean, yes, the event to eventually make landfall, because some of them will not make landfall. So it's a complicated problem combination with both track and intensity. And then in the panel E, we have the landfalling intensity distribution, which is also overly compares overall captures the big picture between synthetic and observed. So that's that. And this all falls into, particularly the second experiment, falls into the ongoing research project within my research team. So here we are developing something called RAFT. It's a risk assessment framework for tropical cyclones. And this second intensity model, the 6-hour intensity model, is part of the toolbox that we are using to generate synthetic tropical cyclones. And I guess the last thing that we recently discovered is that we were originally not designing the second model to reproduce historical events. We were not thinking that it would have enough scale to reproduce history. But we recently did an experiment on Hurricane Irene in 2011. And on the left side, we saw the observed track and the intensity being color-coded. And surprisingly that using this lightweight model, and then propagate every 6 hours, we were able to reproduce events fairly similar. Our approach, it intensified over this region, and then it quickly dissipates as it approaches the mid-Atlantic. And then on the time series plot, we can see that the two compared fairly well as well, which is a kind of surprise. And this inspires ongoing research to use this framework to reproduce more historical events. So that's that. And yeah, and another last thing that I want to mention is that our data and code has been made publicly available in my paper, and so one of the important objective of this study is that we create, because finding the right data for the right problem is the biggest challenge. So we kind of narrowed down the problem a little bit to use ships data and this set of ships data to make these predictions. And here the predictors we believe would be very valuable for other researchers and maybe even students here in Bronze to look at an experiment. And then we can compare with my benchmark models, and we really see a lot of potential that the community can make more contributions to the operational forecast and not just to leave it to agencies. So that's all that about the talk. I guess the one last note I want to mention is that as you can see that a machine learning model or deep learning model doesn't have to be super complicated to be effective. And here we used a existing statistical model. We used a very simple deep learning approach, MLP, and we are able to get some really good result and make a good contribution. So I think this would inspire students who are interested in making a contribution in this area to to applying more deep learning or machine learning approach to do good for the society, like tropical cyclone events forecast. So that's all I have. I will handle it back and see whether there's any questions.
Thank you, Wenwei. This was actually an excellent talk, and I think the weekend, this week was the best week because we have the COP26 conference starting over the weekend about climate change. So I think a perfect discussion before that. We could wait for the questions from the audience.
Glad to hear.
Okay, I'll ask a question. Wait. It seems to me that you kind of, well, my first question is, did you just get lucky, or why your method worked? You didn't tell us.
Oh, why did our method work? I think the biggest, the technical challenges, as you can see that, like having a, using an MLP method is kind of very straightforward, and it's the most simplest model. Once you plug it in with automatic architecture and hyperparameter search, then you are almost guaranteed to get some good model result. The biggest challenge would be to finding the right data set for the right problem. That's the biggest challenge. So I did go quite off track in the very beginning of the project, trying to make my own predictors to forecast this problem. And I even go further to using convolutional neural networks, using 3D field of the tropical cyclones and stuff like that, but didn't get anything. And then, but once I used this approach, it worked. Does that help answer the question? Is that,
I was going to ask about CNN because that has been used before and GANs, but if I were to do this, looking at your data, I would have taken a sort of multi-fidelity approach, just like the last model that you showed, that they take
the consensus model.
Yeah. Why? For example, why don't you use this to train? Why don't you do the same thing for? Why do you commit to ships? Since it's not the best model, why don't you take a multi-fidelity training approach for the neural network, and therefore you will be more robust?
That's a really good comment, and that exactly can be the next step for the biggest improvement. I guess at the beginning, our research focus was narrow enough so that we just wanted to look at one model and prove that this model in the operational forecast can be outperformed. And but exactly, I mentioned that in the paper as well. So that's the next step, and definitely would get some promising result as well. Any additional questions? Do you have any additional question?
No, well, it seems to me that you got a little bit lucky because yes, of course, I appreciate the difficulty in putting together these data sets, and of course, 56,000 of them. But I don't think that you fully exploited the available machinery on neural networks.
That's absolutely.
For example, what's the point of predicting without uncertainty? So that's why I mentioned the GANs. I think having a GAN network there would have helped you to predict with the uncertainty, because you made a good point about the intensity that, although you can track the path, the intensity, even for the last case, the Irene hurricane, I could see that you were not exactly tracking the intensity. So we know that. That's a difficult, but I was wondering if that's, I mean, in terms of competitors, right? And what other groups are doing? Are just taking a off-the-shelf neural network? They prepare the data. If you did a very good job on preparing the data, therefore you discover these correlations. That's basically what you're doing. You don't bring physics into the neural network. You don't bring uncertainty. You just get lucky. You get very lucky.
No, I mean, it's not. Maybe you can call it lucky, but at the same time, essentially the first study, the first step, and what you discussed could be the next study. And what you, I fully admit that, I haven't fully explored all the potential that I can use from neural networks. But because the first batch of result is kind of publishable, and it is then it is put out there. And I would be very interested to talk with you offline to take your suggestions, and maybe even your student may be interested in looking into this problem, and we can work together too.
We have been talking with Ruby Leung, and Themis. He was logged in. I think he just signed out, but about actually the mid-Atlantic hurricanes and how we could possibly tackle this problem. But a couple of weeks ago, I think DeepMind published a paper on predicting the rain with radar data only, and a 2-hour window, and that seemed to be a breakthrough paper. And
you are talking about, is it estimating the current intensity or forecasting the intensity?
No, predicting the rain using radar data.
Oh, predicting the rainfall. Okay. Oh, yeah. Okay.
And so that's different, of course, from what you're doing, which is sort of retrospective studies. But so there are no other groups around the world that, like the Met Office in London, in UK, are usually very advanced. They don't.
I mean, so there are some studies. There are 2 studies that I found. So one in UK, probably in UK. So they did explore many different methods to doing the forecast. But of course, everyone is using different data sets. And I guess from that perspective, I now realize why you say I'm lucky, because everyone is using very different data set, and then some would just not work. Didn't work very well, and it didn't even support in independent reserved test. If it doesn't surpass the parent model, then that's not useful, right? So that's what I observed. One study using the H-Wolf predictors, and then it didn't surpass H-Wolf in the end, which was interesting in independent test.
I mean, your results that you show, the 2019 and 2020, which you didn't include, there was basically a total extrapolation, right?
Yeah.
Right. So that was kind of surprising. It suggests that actually there are very strong correlations from year to year, and that's There's no magic. We work with this system, so we know there's no magic. Panos, what do you think of the study? Did they get lucky, or because I mean, it's not like 4 layers and so on, tune a little bit the architecture. Panos, you there? Maybe not.
So, okay, yeah. Anyway, I would be very interested to chat further with you, or if you have additional research ideas or student interested in this, do let me know, and I have my email there. Anyone interested in collaborating and discussing or brainstorming, I would be all for it.
Yeah, thank you very much, Wenwei.
Yeah, thank you.
谢谢。
Thank you, Wenwei. So it's time we introduce our next speaker, Dr. Aditi Krishnapriyan. So Aditi, you may want, yeah, you're muted. We cannot hear you.
Oh, great. I can go ahead and share my screen.
Yeah, but I'll quickly introduce you to the group. Just give me a second. Yeah. So our second speaker is Dr. Aditi Krishnapriyan. She would be talking to us about characterizing possible failure modes in physics-informed neural networks. A quick introduction about her. Aditi Krishnapriyan is the 2020 Alvarez Fellow in Computing Sciences at Lawrence Berkeley National Laboratory and UC Berkeley. Her research interests include integrating domain-driven scientific mechanisms, modeling with data-driven machine learning methods to accelerate and improve spatial and temporal modeling. Previously, she completed her PhD at Stanford University, where she was supported by the Department of Energy Computational Science Graduate Fellowship. During her PhD, she also spent time working on machine learning research at Los Alamos National Laboratory, Toyota Research Institute, and Google Research. Yeah, so let's welcome Aditi, and you may want to share your screen, Aditi.
Great, sounds good. Thanks a lot for the introduction. Great, and can you see my whole screen?
Yes.
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 Great, thanks. So great, yeah, thanks a lot. Looking forward to being here. Before I get into the details of this talk, I'm gonna actually reframe this more as a talk around rethinking physics-informed neural networks, which was actually how this work started originally. Essentially thinking about the general approach of this powerful tool of pins and the standard machine learning training that it uses, and how we can rethink some of the ways we do the training and the learning for better performance. And I'll be talking about the details of this work that will be appearing at the NeurIPS conference later this year. And this is with a mixed group of people out in Berkeley, like myself, as well as some people in Utah, including, I know, a former student out of the Crunch group, Mike Kirby. Now, usually I have some introductory slides on modeling spatio-temporal behavior and physics-informed neural networks, but my assumption is that this is an audience that's very familiar with both of these areas, so I'll be a little bit more brief here and just mention some of the motivating problems in my area in particular. And so I come from this background in solid-state physics, and some of the tools that we use there are things like atomistic simulation, such as, for example, the molecular dynamics simulations that you see here. And of course, more accurate, faster modeling of this phenomena would be a huge game changer in this field, among many, many other fields. And so at a very high level, I'm interested in these different ways that we can use machine learning to accelerate our simulations, particularly by combining physical insight with these data-driven methods. And instead of throwing out all of the domain knowledge that we have, I think there's a lot of active research going on how to integrate domain insight with machine learning. But I think there's still a lot of challenges and limitations. One of those things is, of course, we are more limited by data, even in some of the cases, in scientific cases where we might have a lot more data, like climate science or particle physics. But also, it's also a little bit of a question of how do we respect spatial or temporal constraints, and how do we respect that information? And so, for example, this is generally an area that I've been working on. And one of those things is, like, in the past, we've incorporated constraints to respect spatial invariance through topological methods, in addition to these other physics-informed approaches. And things like that, for example, incorporating spatial invariance constraints can actually really improve accuracy and transferability for different prediction tasks in either biomolecules or materials. And so things like that, I think, are really what I think are the keys to accelerating some of the scientific machine learning. including things like also looking at numerical integration structure and seeing how we can incorporate that type of structure into some of our problems to learn continuous physics. And so similarly, this is really one reason I think physics-informed neural networks are of interest, because this is a way to add the PDE constraint into a problem, a way to actually enforce or try to enforce that your model is respecting the physics in a given problem. And as I think many people have probably seen, traditional machine learning methods don't always transfer super well to scientific problems. And so in that same way, I think there is some need to create these new algorithms for scientific problems. And so I think, again, as everyone knows here, modeling a lot of different types of spatiotemporal behavior can be quite slow. Numerical solvers might need to take very small time steps, for example, have a very fine mesh discretization to get good error and not blow up. And so this really very interesting idea of physics-informed neural networks aims to model differential equations, essentially solving the solution space all at once by adding the PDE constraint to the loss term. And of course, I know this is something that I think everyone here is familiar with, has been working on for years, I'm sure. And I write it here as this optimization problem. So in this sense, or putting it into this optimization format, we want to minimize some loss, given that we have some type of observational data. Maybe that's the initial condition. Maybe it's also the boundary conditions, depending on what those boundaries are set to. And we want to minimize the loss on those training points such that we enforce the PDE to be 0 at the interior points, the collocation points. And so I've just written it here, something like this, where we turn this constrained optimization problem and relax it into an unconstrained optimization problem. And then the PDE constraint is this soft constraint acting as a penalty. And then we do standard machine learning training on top of that. And you can take this loss on the PDE constraint term, since you know that it should be 0, or you can put it into a format such that the PDE residual should be 0. And so this is very, as you all know, this is very popular, very widely used in scientific scenarios. And I think there's so much active work going on in this area. And here's just another way to display this problem. This is a simple transport equation where we have an initial condition that we do know that we fit exactly to, and then a differential constraint that we know needs to be respected at these collocation points in the interior, and then also some constraint that respects the boundary conditions, whether that's observational or something else. And as you all know, we try to optimize over all of these things. And by doing this, the neural network can actually learn the state space quite well and actually solve the problem. Whereas if it only had the initial condition or only had the boundaries, it would not do so well. So this is this very nice idea of adding this PDE constraint here. And so like I noted that this is it's a cool idea. We essentially came into this wanting to investigate the PINs approach further on a few different applications, scientific and engineering applications that we typically see in day-to-day phenomena. And before I get into the details of that, I just want to take a brief moment to note that there are other types of these investigations that have been done, whether it's for a specific problem or maybe more generally, including investigations, many investigations not on this list that I include here. And since there's so many people working on PINs and for so many different applications, it can be hard to keep up with it all. And so I'm glad to actually be here in situations like this, talking to people like yourselves to also learn more about what people have done or what your perspectives are on these types of problems. And I think the investigations that I'll now talk about here are complementary to a lot of the works that you see here, and potentially also orthogonal or just different ways to look at PINs, different perspectives to look at PINs. And I think that's really the very nice thing about this area, that we all come from different backgrounds, whether it's physics, applied math, computer science, and so on. And so we look at these problems from different perspectives. Now, coming back to this slide, in this talk, I'll talk about our perspective on investigating pins for different problems, and including these common scientific use cases like the convection problem, and reaction diffusion problem. So these simple 1D linear or nonlinear PDEs and ODEs, where we have a convection, reaction, or diffusion operators. And I'll go briefly through each investigation. So the first example that we looked at was 1D convection with periodic boundary conditions and a simple initial condition of sine of x. And note that there is an analytical solution for this system, so we can at least compare it directly to that. And then the loss function is then formulated as you see here with this initial condition term that matches the loss exactly, a PDE constraint term where we're enforcing the PDE on the interior points, and then a boundary term where we try to enforce the periodic boundary conditions. So we don't know what the actual solution is at, for example, x equals 0 and x equals 2 pi, but we know that they should match, and so we can just put a loss on that. And so from this type of investigation, we found that at low values of beta, the speed of propagation, we can learn models with fairly low error. However, as beta increases, the error also goes up. And in this case afterwards, I actually did try playing around to some extent with some of the other tools people have come up with and created, like dynamically changing the multipliers on the loss term. And I found that it actually didn't seem to make a big difference in improving performance, though I didn't look at this extremely extensively. With that said, these approaches do work for definitely other cases. And so I think it can really depend on the problem that we're trying to solve. And so this is what an example heat map for this problem looks like when we have a beta of something higher than 10, like 30. And it's actually, I think, a quite interesting heat map because you see that the pin is able to still match the boundary conditions up to a certain time, but then it's still matching it actually beyond the whole way. It's just that the interior is, it's not getting the rest of the interior.
Aditi, can I ask what's your loss function?
Yeah, so the loss function here is this function that you see here on this slide.
So, okay, but that's not what we use. I mean, you're not, what is lambda I here?
So this is right. So in this case, the multipliers on the loss function, they are all the same. So we treat it as initially, we just do the original approach of keeping the multipliers all the same. I agree that dynamically changing
but what is it? What's the value? Is it 1.5, 100? What is it?
It's just 1.
Oh, it's all ones. Okay. So there's no, actually, there's no lambda i's.
That's right. Yeah. I put it here because I'll talk a little bit about that later on. But for this case, yeah, it's 1 here.
Okay.
Great. Yeah. So so this is just one case of that. I'll go to the next slide now. And just continuing on that note, this is just a few example heat maps of what's going on. So just different beta values. And you can see that beta equals 10, it's still doing quite well. It's just once we get higher than that and move faster and faster.
Can I interrupt for a moment? Can you go back to the loss function for a moment?
Sure.
So what is the first term?
So the first term is the loss
Just
on the initial condition.
Initial. Okay, yeah. You have B for boundary, but you don't have I for initial. So I was wondering if you're okay, fine. Yeah. Okay, sorry, go ahead.
Yeah, no problem. I should have been more specific that this is initial, this is the PDE constraint, and this is the boundary term. Great. So the next problem that we looked at was looking at reaction with pins. This is just simple ODE, the reaction term in Fisher's equation, again with periodic boundary conditions. Again, lambda is 1 here, and I do want to make a note. In the last case that I showed convection, dynamically changing the lambdas didn't make a huge difference on these losses, but in the reaction case and the next case I'll show reaction diffusion, it does help. So it depends on the problem. But for the purposes of the investigation I'll go through, I'm keeping the lambdas all at once, all at 1.
Just being picky on the word, you're learning the reaction equation or you're solving it?
Yeah, you could say solving reaction with pins.
Yeah, thank you. Yep. Okay.
Sure. Great. So in this case, the general pattern was as the reaction coefficient increases, the error also increases. And these are just some example heat maps of what that looks like at higher reaction coefficients. And I do want to note that this idea of pins having more difficulty learning sharp features in the solution has been noticed before. And I think to some extent that is what's happening here, where as we go to these higher reaction coefficients, the solution gets sharper and sharper. And again, like I mentioned, while dynamically changing the weights didn't seem to help as much for convection, it does help for the reaction case, as well as the next case that I'll talk about. So again, going a step further beyond reaction, we also looked at modeling a reaction diffusion system, in this case, Fisher's equation with pins. So now adding in this diffusion operator term. And I'm particularly interested in these types of reaction diffusion systems because they're common in studying phase transitions in condensed matter physics, as well as general chemical kinetic reactions. And so that's where some of my interest comes in looking at these types of systems. And since everything dissipates quickly with diffusion, we add this reaction component. And you can numerically solve for this problem. You can numerically solve a solution for this type of problem just doing something like Strang splitting. And so the loss function now looks something like this, very similar to before, still periodic boundary conditions, still a loss on the initial condition, and then a loss on the PDE constraint, which we know should be enforced at all the interior points. And so here are a few reaction diffusion example predictions with pins. This is just where the diffusion coefficient is changed. In our paper, we include a few more cases of different diffusion coefficients just to give a feel of how the solution changes when we change some of the parameters in the problem. And so just to summarize what I've gone over, and again, this is something I think people have seen in maybe some of these systems, maybe some other systems. We essentially looked at these common differential equations with convection, reaction, and diffusion operators. And the pins can be sensitive to the ODE and PDE coefficients, particularly if there are these sharp features in the solution. And then in the next part now, I'll talk about how we've looked at and characterized some of these challenges, particularly looking at it from maybe an ML point of view, and then how we've also tried to change the learning paradigm as compared to the standard ML training and how that can make a difference in the performance that we see. So to better understand and characterize what's happening, we adopted this loss landscape perspective to better understand and see what's happening after we train a pin model. And so in this case, this is the 1D convection equation. We train a model and then we perturb it in the direction of the top two Hessian eigenvectors, and then we plot the loss landscape. And as you see here, we see this issue right away that at these low values, these low wave speed values, our error is quite good, and the loss landscape is also quite smooth. But when we go into regimes where our error gets higher, like beta equals 20, 30, and 40, you can see that the loss landscape gets very complicated as we move there. And in particular, like beta equals 30, for example, it seems like a very difficult landscape to traverse to try to figure out where the right solution is.
Excuse me, this is Lulu. Yeah. So how do you train the network?
Yeah, so in this case, the network is just trained to minimize, the loss that I showed on the previous page. All it's doing is running a network to minimize that loss.
Yeah, I mean, what algorithm, Adam or?
Oh, right. Yeah, so in this case, this is using LBFDS. So
directly using the LBFDS.
No, that's right. Yeah.
That could be issue. Yes. Okay.
That's not right, Aditi. That's not how we do it. I think you're comparing apples and oranges.
Sure. So one thing is I did try a bunch of first order optimizers, and also I tried Atom and then moved on to LBFTS. I actually found that somehow using LBFTS directly seemed to actually give the best performance, as opposed to starting with a first order optimizer and using that, or starting with first order and switching to second order. But I'm sure there are more intricacies here to the training strategy.
That's fundamentally wrong, because the second order, the LBFGS, is basically quasi-Newton, and
Sure.
For Newton, even for finding the roots of the polynomial, you know that you have to be, if you're not in the neighborhood, you're going to go to the wrong neighborhood. So you have to be in the neighborhood. So you cannot use in a landscape like that, in any of them, the LBFGS to start with. I mean,
sure. So,
I'm not saying that the point that you're making is not a good one, but I think you're not using all the available tools to get there.
Sure. So I agree with you that so like I mentioned, there were some approaches here where I tried starting with something like Atom and then switching to LBFTS, or even just trying Atom for many iterations. In this particular case, it didn't seem to make a huge difference, but I think you all have looked into this training quite closely, and so I think, yeah, you're right that it makes sense to try other optimization strategies as well.
This is Stefan from UPenn.
A very naive question. What is epsilon 1 and epsilon 2?
Epsilon 1 and epsilon 2 are the amount of perturbation we do in each direction. So we train the model, then we perturb it in the direction of the top two Hessian eigenvectors, and up to a certain extent, and then we plot the loss based on that. So epsilon 1 and epsilon 2 are the amount of perturbation that we do.
So when you say that this is the landscape, it's not so easy for me to understand why you would think of that as the landscape. This seems to be the perturbation in two directions.
That's right. Yeah. So one thing is that it is hard to quantify a landscape in all of the directions. Yeah. And that's the reason why we pick instead of picking random directions, we did pick the top two.
No, that makes sense. I understand. It's just that I mean, you call it the landscape, and it is a landscape, but it's not clear to me how I should think about it. Anyway, okay, thank you.
Sure, and I think if you really want to do a landscape analysis, you do have to look at it in all the directions and analyze the topology of all of those directions.
I understand. That's why I'm asking what I should see when. So if things were normal, you would expect that you would have like a nice parabola. I mean, like some paraboloid or something.
Right. So you see that for like the beta equals 1 case, it's a lot smoother, right? And looks it's a little bit, seems like an easier landscape to traverse, whereas in some of the higher cases, you see that it's not very smooth.
Okay, thank you.
Can I ask one more question? This is Stefan from UPenn. So what's the weights you use here? Basically, those weights will essentially determine the loss landscape.
Right. So you mean dynamically changing the weights will also change the landscape?
So you mean they are dynamic changes, then those the OIC. Okay, thank you.
Thanks. Great. And I'll just also show this slide as well with, again, the same type of thing where we train the model, perturb it. And this one is just looking at the trade-off between how much PDE constraint we add and what the landscape looks like. And I think I realized I didn't put this here, but this is for the 1D convection case where beta is equal to 30. So a case where we have an idea of what the error is. And so again, you sort of see this same pattern that when there's very little PDE constraint, the landscape is much smoother. And as we add additional constraints, it starts to, again, in this particular case of these directions, starts to get somewhat more complicated. So building on the insights gained from the challenges in training pins, I know there are many approaches that people use to try to address some of these challenges. And so the way that we actually looked at addressing them is by changing the machine learning paradigm. And so the two approaches I'll talk about here are something that we call curriculum regularization and something that we call sequence-to-sequence learning. And I'll go through each one now with more details. So this first idea is curriculum regularization. So analogous to how you start learning math, you're probably not going to start with calculus. You'll do addition, subtraction, algebra, geometry, so on, until you get to calculus. In a similar way, instead of immediately training the pin at beta equals 30, which we know is a hard problem where it fails or doesn't do as well, instead we start training the pin at a low beta where it did do well at these low wave speeds, and then we slowly move up the training to the higher betas where it didn't do well when we started training it right away. So we essentially start with a simple problem and we make it harder and harder. And so as you can see here for that convection case, this type of curriculum regularization does end up decreasing error by a couple orders of magnitude. So before, when we did regular training, we would get something like on the left that you see here. And when we do this type of curriculum training, we end up learning the solution for the most part. And I think one thing that's also interesting is that curriculum regularization also decreases the variance in the error quite a bit. And so this is just a table showing some of the errors for regular pin training versus this curriculum training, and you can see that it's lower. But I think this right plot looks at the error over a bunch of different initializations and just plots the error for each one. And so here you can see that this type of curriculum training also just generally shifts the whole variance and the whole the mean and the standard deviation of the error down in general, not just for one given case. And coming to the reaction case, recall that higher reaction coefficients, the error got worse. And so we can do the same thing here as for the convection case, where we train the pin with the easier problem and then move up to the harder problem. And so after training the pin through this type of curriculum regularization, we see again that the error is a lot lower for the high reaction coefficients compared to before. And I show an example heat map here when the reaction coefficient is 10. And so you can see that now by doing this type of training, we can actually capture the sharp features in the solution in the bottom figure there. And so additionally, coming back to this loss landscape perspective, here's the loss landscape of a trained model using the regular training approach. This is on the left, the figure that we saw a few slides ago. And then on the right, this is the curriculum training approach, where we start at some simple problem and we slowly move up. And so you can see that the landscape is much smoother now for curriculum regularization. Of course, the error is much lower. And so the right is sort of the type of thing that we'd like to see, where it's a little clearer that it's easier to optimize there. And it's easier to get to a point where we actually have good error. It's an easier place to traverse, essentially, is where we ended up at, versus something like what you see on the left here.
So I'm a little, okay, so again about this. I mean, these are, if you want, they are linearizations around different places. Right? I mean,
sure.
So in what sense do we compare something that is?
Yanis, I think this is what you call in dynamics continuation methods.
No, I understand, but what is the relation of the curvature of the Hessian at one minimum versus at another one, right? The one on the left is a minimum that is not a good one. The one on the left is a good minimum that has been obtained through continuation. You seem to suggest that a bad minimum has a bad landscape and a good minimum has a good landscape. Do I make sense? I mean, it's not as if you have two methods that give you the same thing with different properties. It's a different thing on the left and a different thing on the right.
So the idea of this is mainly to illustrate where we end up after some type of training, and essentially show that by doing one type of training, we can get to a much smoother landscape than by doing another type of training. And that smoother landscape essentially implies that it's an easier optimization problem.
But am I not right in saying that these landscapes, they are landscapes of the same problem? It's just that one comes from linearizing around one minimum, and the other is about linearizing around a different minimum.
Right, so they are for the same problem, and exactly, it's just a different way of training one model versus training the other model.
Okay, thank you.
Thanks.
Hi, this is Apostolos from Brown. Yeah, in general, there is a discussion in machine learning that different optima, when you study the landscape, even in those two directions, when you study the landscape at these two different optima, then you can say something about the whole optimization, even though you converge to two different optima, and even though the loss landscape is completely different, you can say something about this optimum by using this visualization tool. So yeah, what Professor Kyriakidis is saying is true, that this is what we are saying here, but yeah.
Right, yeah, no, exactly. You're completely right. That's the general trend, that even by looking at this snapshot, it can at least still give us an idea of what the optimization problem is like and how potentially easy or difficult it could be.
Yeah, and I agree. Yeah, thanks.
Great, thanks.
Aditi, I just want to tell you that people are interested. That's why they are asking this question. Okay, don't take it personally. It's a good thing that people are asking.
No, we are interested. Of course. Yeah.
No, I completely understand, and thank you everyone for asking these questions, because I think these talks are more interesting when there's actually a discussion going on. It means people, and I really welcome the perspective that everyone is asking or giving with their questions. Great, so that was curriculum regularization. So the other thing that I'll talk about is this way of solving pins. So another thing, as you all know, is that it tries to solve the whole state space at once. So we just have initial conditions, boundaries, interiors, and we make a prediction on the whole state space. And so one of the things that we looked at instead is, what if we make a prediction segment by segment? So in PDEs, it's common to use these time marching schemes to go solve them by going across the time space. And we try something similar here with pins, which I'll call sequence to sequence learning. So again, the assumption is that we assume we only have the initial condition at t equals 0. It's very possible in many cases you have more data than just at that point. And so now we train a model, but instead of training it for the whole state space, we only train it up to a certain delta t. And so we just focus on this space from 0 to delta t. And then we use that prediction, that predicted solution at delta t as the initial condition for the next time step. But we're still doing pins training. It's just that we're breaking up the time space into multiple blocks. And so that looks something like this, where after we train the model for one time block, one temporal segment, we then use the predicted solution at the end of the time block as the initial condition for the next time block, because this is again under the assumption that we only have the initial condition. And so we can continue to do this. And essentially, we march across the state space one temporal segment at a time until we get to the end. And now we have the prediction across the whole domain. And so the general gist of this type of method is that it does end up decreasing error a lot for the systems that we looked at. In particular, I show this reaction diffusion example here, where you can see that reaction diffusion actually ends up giving a pretty good solution now. Again, with the same type of loss function for pin training, but we've broken it up into multiple temporal segments.
Sorry, can I ask a question?
Sure. Sure.
This is Nat from Sandia. So when you go from segment to segment, do you have one global neural network which is persisting across all segments, or does each segment get its own neural network that's being trained?
Yeah, great question. In this case, it's one global network that's persisting across each segment.
Got it. Thank you.
Thanks.
Hi, Aditi. It's Amir from Brown. I have one question. So are you training these sequence to sequence one at a time, or since you're feeding the you're generating a new initial condition for the next layer, so are you training it one at a time or parallelly, all of them?
So they're trained one at a time. So one temporal segment, then we use that information for the next temporal segment, and then so on as we keep going.
Okay. Thanks.
Yeah, thanks. And I know there are domain decomposition approaches that are more analogous to training different segments parallelly.
Yeah, that's true. Yeah, thank you.
Thanks. And so here's just a table of numbers for the sequence approach versus predicting the entire state space. This is for the reaction diffusion case. The reason I show this type of segment, though, actually, one thing I think is interesting about it is that you can note that there's this trade-off between how small the time step is, how small your temporal segments are, and what the error is. And I think partly some of that is because if the time step is too small, then your error can end up propagating, because we have this assumption that we only know the initial condition. And so I just thought that was interesting, but also because in many real world problems, we have more data. I think that can also change how you pick the time step for this type of sequence to sequence learning. And again, I'll show this example for the reaction case. And so you can see here, once again, that this sequence to sequence approach does decrease error a lot for the reaction case. And it also does help with the convection case. But in general, we found that the curriculum regularization approach tends to work better for that case. And so finally, just to give a summary on this analysis for pins, I think as I think everyone here knows, this is this very promising, popular method. It can work well for a lot of scientific phenomena. And so we just took this approach of analyzing it for common scientific problems like convection, reaction, and reaction diffusion. Again, I want to point out that other people have also analyzed pins for different problems or other cases. And so I think this is really complementary to that work and potentially a few orthogonal solutions. But I know that the true I think the true solutions here will come from a mix of all of these different methods. And so this regularization term, the PDE constraint in pins, can make the landscape hard to optimize, as you saw with some of those landscape figures. And so the general gist of this was also to this idea of rethinking the standard machine learning training. By changing the learning paradigm, we can greatly decrease error, whether it's with curriculum regularization or sequence to sequence learning. And I think there are also cases in the real world where we'll have more data than just the assumptions we make about the initial condition, and data assimilation is easy. So all of those things can play a role in the performance of these models. And I figured since there would probably be discussion, I wanted to also finish at this point to also give time for discussion and any other questions or comments or feedback people might have. So thanks a lot.
Thank you, Aditi.
Can I ask, I guess you may have trained a whole bunch of pins to do this kind of comparative analysis. Can you give us some idea of how long you wait to train each one? how many you do and on what hardware?
Sure, yeah. Happy to provide that information. So this is typically for each of these pins problems. This is typically training it with a few different parameters. Some include like the learning rate, and that depends on if we're doing just LBFTS or doing Atom and then LBFTS or whatever combo of optimization that we do. The other thing that I also varied to get a better feel was actually changing the initialization seed. So just starting with different seeds and averaging them over, say, like 10 different runs. And the reason I think that's interesting is because one of the figures I showed earlier, you see that occasionally for one seed, it might find a good solution, but just not as consistently. So that was the range of different experiments. Also, different experiments run at different PDE and ODE coefficients. So like the reaction case or reaction diffusion or convection, those coefficients were changing during these experiments. And this was all run just on, most of this was run just on one GPU, but often trained in parallel, so different experiments running on different GPUs. This was, depending on the problem, this was a Tesla V100, or actually no, one of the more recent Tesla GPUs.
How long do you take per training run? Like not a whole hyperparameter optimization, just one run?
It depends on the problem. So if the problem is a harder problem like convection, high beta, then it can take some minutes. Maybe a single problem would take a few minutes, so nothing too on the high end. If you have an easier problem like a lower beta, then you can get it within usually about a minute or two.
Thank you.
Thanks.
Hi Aditi, it's Samya again. Just I was curious. What's the advantage of this sequence-to-sequence learning over the domain decomposition-based pins? Because if you can solve the same thing parallelly, why do you want to solve it serially, right?
So yeah, so I'm not an expert on the domain decomposition approach, but one of the advantages of solving this problem sequentially is actually that we can train a temporal segment and then use those weights that we trained to initialize the next temporal segment. So we're giving it a much better guess across the domain. And I think that actually ends up making quite a large difference. So that's, I think, the biggest advantage of training it sequentially.
But when you go for a big problem, then this will take really a lot of time when you go for sequence to sequence, right?
So,
it's good for a toy problem like the one you have shown, but if you are going for a really big problem with big data, then going sequence to sequence, I think it will be even more costlier than the original pin, the vanilla pin approach.
So that's right, that it is more expensive because we're doing these segments. It's not as expensive as you would think because of that extra initialization component. So every segment actually, once you train the first one, it actually converges very quickly because you've given it a very good guess for the next one. I agree that for these very big problems, it would be harder and take longer. But I think one thing is getting the error down, making sure it works for these cases, and then we can think about scaling it up at higher levels.
There's also there's an advantage in terms of the regularity across the boundary of the subdomains, right? So if you're doing an X-pins thing where you're gluing it together, you basically have a discontinuous solution that pops out, right? Because you're just penalizing the mismatch. Whereas this will give you as much regularity as you have in the activation functions. Right?
No,
So
that
is an advantage
that can be tackled with the dynamic weights. I mean, that's what we have seen. If we use the dynamic weights across for the interface, then we can actually reduce the jump in the solution.
Well, you can make it smaller, but it's always going to be there, right? So there's some problems where you can't have that, right? Not that not that I'm saying that there's just certain cases where this might be valuable.
But I think it will be true for this case also, because when you pass the initial condition for the next block, that is still a data for the next the network, right, to fit. So you may not be able to fit it exactly. So you still get a jump, right? So maybe it will be more clear if we can see the error plots for the sequence to sequence compared to just a solution plot.
Sure.
Yeah, that's just a comment. Yeah. Thanks, Aditi. Thanks.
Sure.
I kind of have a related question. So I really like the idea that you're continually you get a good guess to help train later on, right? So you're kind of propagating your good guess. But have you identified, there's a situation you could run into where you use all the expressivity of the neural network to approximate your initial condition, right? So if you train just on the first batch, right, it can pull all of the activation functions all the way to the initial condition. And then as you propagate forward, it can pull those activations back, right? Like, so you need a very big and a very over parameterized network in order to make it so that you're not forgetting the initial. Have you run into anything like that? I'm not sure if.
Yes.
I'm something very specific in mind. This might not make sense if if you haven't run into this before.
Sure. So I can on that topic, I can just give you some just what I've experienced with this type of problem. And one thing actually you touched on that I think is an important point, and something that I think some of this study shows, is the idea of expressivity versus optimization difficulty. So a question when you might look at these problems and you see the error might be, well, I mean, you're just using a very typical neural network. Maybe you should make the network much bigger, much wider, and it'll do better. But I think one interesting thing about these types of studies, whether it's the curriculum one or this, is that actually the neural network has the capacity, the expressivity to find the solution. It's just a hard optimization problem. So it's not able to get to those points. And I should have actually included a loss plot, but you can see for some of these cases that the loss can actually get relatively decently low. And so it's actually, it's more related, I think, to the optimization problem. For the case that you mentioned of you might need a really big network, I think, yeah, that I think would depend on the problem. If you're doing much harder problems, I imagine you would still need a larger network. But I think one of the things that popped out to me from this type of study was that in a lot of cases, even not super huge networks do have the capacity to find the solution. There's just other things getting in their way that we need to overcome. And maybe we can talk more about a use case you had in mind or something, because I'd be curious to know more specifics about where your question was coming from, because it sounds like it was more related to a specific case.
Sure. Thank you.
Thanks.
I have a question about the first part, which is, as I said, this is known as continuation methods. The problem is that you're looking at something which is kind of smooth and boring, although pins fail, the vanilla pins, but there are many ways around it. The interesting problem is when you change this parameter, which is basically your bifurcation parameter, you may run into bifurcation. In other words, a dynamical system, nonlinear dynamical system, including the nonlinear reaction diffusion that you showed, could go into another state. So there's a branch point, okay, like a whole bifurcation or something like that. So your continuation method will break down there. So your curriculum will go down. It's like going from elementary school to first year in college, and that would be a shock.
Right. And
so how do you deal with that gap in knowledge?
Yeah, that's a great question, actually.
Different states. There's no continuation.
Yeah, I'd be actually quite curious to know if there are good machine learning methods that can deal with bifurcations, because it seems like a generally hard problem to deal with. We have a hard time dealing with them even in various numerical approaches. And so do you know of any good ML methods that can actually deal with the fact that there might be more than one unique solution?
I asked the question. I cannot give you the answer.
Sure. Yeah, I guess yeah, no, that's a great question. I think yeah, I mean, I think there are certain things maybe if we have an idea of the bifurcation, if there are ways to detect or know that there might be a bifurcation, maybe we can set up like two problems to account for the fact that there could be two sides of the solution. Maybe if there's a discontinuity. One thing is I would be actually curious to see how the curriculum approach works, even if there is that discontinuity, because we're still starting, like you said, we go from, like elementary school to first year of college, but that's still better than going from a toddler to first year of college. So
well, not so clear actually, because let's say flow past the cylinder, right? You have steady state, and then you hit Reynolds number because that's what you're doing. You're changing the Reynolds number, and it becomes from 40 to 50 or 49. All of a sudden, you get a totally different state. You get traveling waves instead of steady states. Instead of symmetry, you get that symmetry. So there's a different totally modes that you excite. It's a Hopf bifurcation. So there's not gonna, I don't think the steady state is gonna help you.
Sure.
Although you have I mean, I can set up lots of problems for you to, but I admire the way you answer your question. That's why you're an Alvarez Fellow. You answer the question with a question.
Yeah, it's actually something I've been quite curious about, and I think I think there's two things that come up here. So one is that what's the best way to do the curriculum training? It's, I show these examples where the coefficients change, but maybe there's better ways we can come up with a better curricula. And the other thing is that I am actually very generally curious about how we would deal with bifurcations in general. And so any machine learning literature on that would be very interesting, I think.
Do you know Johan Tang? He's another Alvarez Fellow.
Yeah, I was actually just going to mention him. Yeah, I do know Johan, and he's still at Berkeley now, actually.
Yeah, he's also a Crunch member.
That's right. Yeah. I talked to him about that. I know he didn't work on pins specifically, but there are definitely we did a proposal together and a few other things, so we definitely have overlap in our research.
Because there's several people who are working on this type of things here. Sifan was, and Meya and you and others, with self-adaptive weights, there's adaptive activations, there's domain decomposition. Somebody should evaluate all this and on the same problem and come up with some sort of guidelines. I think that's a worthy effort to. And this, of course, could work synergistically, because there are lots of people who, we actually invite lots of people here in this seminar series to tell us how bad pins are, and we are used to it. So negative publicity also increases our citation.
Yeah, and this is sort of why I also said in the beginning that I don't think I think it's a really interesting and cool idea. I mean, that's the whole reason I was interested in it. So I definitely didn't want to come in here being like, oh, you have to do all this. I think there's so much, yeah.
No, just kidding. Thank you very much for taking the time, Aditi. It's good work. And
yeah,
congratulations for the paper in Europe. Yeah, that's difficult to get a paper.
Yeah, thanks so much for all of the questions and the discussion. I like I said, I completely agree with you that I think it'll take a mix of methods. These are synergistic, even different comparisons of how you optimize, for example, how you use the methods would be really interesting. So I'm glad to have had the opportunity to talk here to learn more about those and the work that many of you do to push this frontier.
Okay. Some data.
Great.
Well,
thanks.
Back to you. You're there.
So thank you, Aditi. Thanks a lot. So with that, we come to the end of this week's Crunch seminar. We had two lovely discussions on pins and on tropical cyclones. And I wish you all a very happy weekend and a good rest of the day. Thank you.
Thanks, Mel.
Thanks.